So yesterday we had found that there is an isomorphism of algebras from the group algebra of a group G. As usual, G will be a finite group. I'm not mentioned this explicitly. And a direct sum, just a direct sum or product of endomorphisms where V1, Vt, let's speak in terms of modules, are the irreducible or simple CG modules. So one for each isomorphism type. Okay, so there is an isomorphism like this. Then, in particular, this isomorphism induce an isomorphism between the centers. Of the two algebras. This is, as I said, an isomorphism of algebras, which means, well, it's slightly more complicated, but that it's an isomorphism of rings, and then also an isomorphism of vector spaces. So in particular, these two centers will have the same dimension over C. So we compare the dimensions of the two centers. So on the right, we will, in this endomorphism thing, remember that this is just a ring of blockwise matrices, okay? So this is the endomorphism ring of V1, this is the endomorphism ring of V2, and so on. And so its dimension, well, the center of each single endomorphism ring is the center of a ring of matrices is just a scalar matrix of size dimension 1. So the center of this will be formed a scalar multiple of a scalar lambda 1, a scalar multiple of a lambda 2, and so on. So it has dimension T, okay? So on the right, dimension of the center T, which is the number of irreducible CG modules. And on the left, we had seen that the center of the group algebra is the number of conjugacy classes of G. Because we had seen that the center, because the center of CG is a subalgebra, in particular is a vector space, as a vector space as a basis, as a base, given by the sums over the conjugacy classes. Of G. Perhaps an example is in order to clarify what I mean. For instance, and this will be useful later when we discuss the character table of S3. S3 has 3 conjugacy classes. Okay, and what are these conjugacy classes? One is the conjugacy class of 1, okay, which is, of course, when you conjugate it and get the same. Then remember that in Sn, conjugacy classes are easier because all 2 elements are conjugate if and only if they have the same cyclic structure. So the other conjugacy class, another conjugacy class is given by the element, by the 3 cycles. in which the cyclic structure is 3, say, and then the last conjugacy class is given by the 2 cycles, because their cyclic structure is given by a cycle of length 2 and a cycle of length 1, which, as usual, we don't write. So what's the center of the group algebra of S3 as a basis? Well, maybe a basis given, there may be, of course, other bases. I write base or basis given by, this is one element, it's a sum over one element, then the sum of these 2, and then the sum of these 3. The reason this is in the center is then when you conjugate, when you conjugate with an element of G, you exchange these 2 or you exchange these 3, but the element remains in the center. Okay, good. So we have this important result. There are a number of reducible CG modules. Since this is important, we rewrite it. So the number of conjugacy classes of G equals the number of, let's say, pairwise non-isomorphic, just to be clear, irreducible CG modules which is the same by the equivalence that we saw between modules and representations, number of, once more, pairwise non-isomorphic irreducible representations of G. And the third number is the number of characters, of reducible characters of G. One of the advantages of character is when it comes to characters, you just have equalities. Whereas you may have several distinct representations, we saw at the beginning, I mean, changing bases, that are isomorphic. Isomorphism of representations translate to equality of irreducible characters, okay? Because since the character is a trace, as we will see in a second, this yields the two isomorphic representation have the same character. The fact that these numbers are equivalent. Oh, yes, okay. And let's add an important thing. Characters of a group perhaps we have already mentioned this, are class functions. That is, the character, if you consider the conjugate of an element, this is the same as the character of a conjugate of an element is the same as the character of the element. Why is this so? Well, the reason is very simple, because the character of this, okay, is nothing else than the trace of the corresponding representation, okay? Where this is a representation. Remember the term that we have used, affording the character chi. Okay, simply meaning that chi to be a character means it's the trace of a certain representation. Okay, representation is a homomorphism. So this is rho of H inverse, rho G, rho H. Okay, and the trace. This is the same argument that we used to see. The two isomorphic representations, which are conjugate in some sense, give exactly the same character. Since the trace of AB, of the product AB equals the trace of the product BA, we can exchange the two factors. Sorry. Okay, We have exchanged the factors, and we see that this is, of course, 1. It is exactly, by definition, the value of the character in the element G. So these are functions. That is, in other words, the character is a constant. Is constant on a conjugacy class. But then this factor has an interesting consequence, because consider the set, the vector space of class functions on G. So that is, of the functions from G to C to the complex number C, which are constants on conjugacy classes. This vector space, let's call it C, script C. Clearly, the dimension of this C equals the number of conjugacy classes, number of conjugacy, number of. Well, let's write it explicitly. Yes, because I mean it's a function between a set, between the set of conjugacy classes and the complex number. So as usual, you can use the delta, the Kronecker delta function as a basis. But then you see that, let's go back here, that the number of conjugacy classes also equals the number of irreducible characters. And we know that the irreducible characters, so the irreducible characters, here G, are contained in C. We just saw that they are, I mean, I'm just restating here the fact on the previous board that the irreducible characters are class functions. But the irreducible characters, this is also the number of irreducible characters, okay? So here G is a symbol that I've used a few times to denote the irreducible characters, but that's a set of irreducible characters. Okay, and we know that they are independent because they are orthonormal. Okay, since the elements of G are orthonormal with respect to a certain inner product, they are independent. And thus, they are a basis. And thus, we can call it a theorem. Here G is a base. I write base or basis of C, of the space of class functions on G. Okay. And remember that we had an earlier result, which is less important to us, which says that if you take all the reducible representations and all the function that associate to G, one of the entries in the matrix, what we call rho I, J, K, they are a basis for the space of all functions from G to C, okay, because they are the right number. And here we find this factor that is perhaps more important in context, but is in this context, but it's a consequence of that the set of irreducible characters are a basis for the space, vector space of class functions on G. Okay, so and this also in fact is a factor that is not obvious at all, because I mean we take the class functions on G, that is the functions that are constant on the conjugacy class, and we think they may be whatever, but they are actually linear combinations of characters coming from linear representations. There was no reason a priori why these characters, these traces should have generate as a vector space the whole vector space of the functions of class functions. The fact that this fact that the number of conjugacy classes equals the number of reducible characters allows us to construct, no, wait, to construct the character table of a group. Okay, this is a square matrix, say. Okay, which has, whose rows are indexed by the irreducible characters of G. And whose columns are indexed by the conjugacy classes of G. And of course, in an entry, we'll find the value of the character on the conjugacy class, meaning on an element of the conjugacy class. Let's start with an example, which is incomplete at the moment. One of the things we'll be doing during this lecture is to build the character table of S3, okay? What we can say about the character table of S3 at the moment? Well, there are three so S3, there are three conjugacy classes in S3, as we saw a moment ago. So I write as labels for the columns, what's this? This is a representative for the conjugacy class. Okay? And then, since we know that the number of conjugacy classes is the same as the number of reducible characters, we know that this must be a 3 by 3 matrix, okay? And here we'll have the values of 3. So S3 will have 3 reducible characters. Okay? There is one more thing that one usually writes. This is the size of the conjugacy class. We'll see why this is useful. So I write 1 because there is only one element in the conjugacy class of 1. I write 2 here because there are exactly 2 elements in the conjugacy class. And write a 3 here because there are 3 elements in the conjugacy class of 1, 2. We saw this in the previous slide. There is something we can always do for all groups. Write the first row, and this will be 1, 1, 1, the trivial character. So what's the trivial character? Well, it's very simple. Given any group, any finite group G, okay, we can consider the trivial character, let's call it tau, well, let's call T, okay, the G from G to GLC, the complex numbers. So this is also that C star, the non-zero element of the non-zero complex numbers. This is the linear group or vector space of dimension 1. So I may take C, and this is simply the representation, then send this to 1, okay? Actually, sorry, to 1 among square parentheses, among brackets. This is a one-dimensional representation, so I get 1 times 1 matrices, and so what are the value of the character? The character is the trace of a 1 by 1 matrix is just the element inside. I'll resume. I'll reprise this elementary element, the elementary argument in a second. Okay, and what we'll see then it won't be difficult. We'll find the missing numbers here. Perhaps there is an important thing that we can already do to show that what the theory we have developed so far already allows us to write down certain things without knowing much about the representation themselves. And this is, let's look at these columns, okay? So in the first column, for a character chi, we find the value chi of 1, okay? The identity of the group, okay? Because the rows are indexed by the characters, the columns are indexed by the conjugacy classes, and I haven't written the third thing down, but what you find here, for instance, the value of the character chi2 on 1, on the elements, oh yes, on the element 1, okay? The value chi1, what's this? Well, if I write rho for the corresponding representation, this is rho of 1, the trace of rho of 1. This is an argument I've already seen, but I mean, so this is the trace of what? Of the identity matrix, because of course rho being morphed in sense 1 in the group to the identity matrix. And so this is the dimension of V, means where rho, let's write it, okay, let's write it here, rho goes from G to GLV, okay? And this is called the degree of the representation of the character. It's a dimension, okay, but also in field theory, we find degree being used for representation. The degree of rho or chi, okay, the dimension. And we have an important result that that is that we have used in proving this isomorphism, that the dimension of these two things is the same. That is, if you take this, which has dimension G, which has dimension the order of G, and you take this, which has dimension of V1 square plus dimension of Vt square, okay? This is something we knew before the isomorphism from the characters. The two are equal. This means that if you look at this column, you should have that the order of G of S3, which is 6, is the direct sum of is the sum of the squares of this dimension. So the order of the group is the sum, just a sum in integer, actually natural numbers, of the squares of the dimension of the irreducible representation, pairwise non-isomorphic, okay? And these are the dimension, the value of the characters, okay? Because it's the trace, so you sum and you get the dimension of V. But we notice that this is 1. And now it's a matter of thinking for a second. If this is 1, this means that the sum of these squares is 6, okay? So if the two are larger than 2, you get at least 4 plus 4, which is 8, too much. So one of them has to be 1 and the other one has to be 4. So these numbers will be 1 and 2, okay? Because we need the sum of the squares to be 6. There's already a 1. So the only way to make a 5 is 1 square plus 2 square. So we know already the dimension of the degrees of the reducible characters, okay? And yes, okay? And then we'll determine the rest with the technology that we are going to develop in the next pages. Just a second. No, okay. So, yes. Let me think in which order I want to do this. Yeah, okay. Let's begin with the theory of the characters of abelian groups. Well, I'll add finite every now and then, but our groups are always finite, okay? The only time non-finite group appear is when you go in one of the seminars in the theory of compact groups whose character theory, representation theory, say yes, is remarkably similar to that of finite groups. Of course, finite groups are compact with respect to the discrete topology. Good. So what we know about, so let G be a finite group, an abelian group. Of order n. Claim which is actually I had already claimed and proved this, but let's claim it again. The irreducible characters of G are all linear, meaning of degree 1. Let's make an observation. I open a parenthesis, hoping to remember to close it. So a linear character meaning of degree 1. Remember, the degree is the dimension of the underlying vector space. So if the dimension of V is 1, any representation rho from G to GLV is irreducible. The reason is that for a representation not to be irreducible, it means that there is a vector space which is different from 0 and V, a subvector space, a vector subspace of V different from 0 and V, which is invariant under rho G. Okay, but here, since the dimension is 1, there is no such subspace. Okay, reason: there is no subspace U such that which is different from 0 and different from V. Okay, for this not to be irreducible, you need to have a subspace different from 0 and V, which is invariant under rho G. Now, the point is, if the dimension is 1, there is no subspace different from 0 and V, because this has dimension 0, this has dimension 1, so there's nothing in between. Okay, so if the dimension of 1, any representation is irreducible, but there are irreducible representations, there are groups and irreducible representations with, instead of and, with irreducible representations of degree, okay, of this dimension greater than 1, close parenthesis. I'll be back in a second, and we have already seen an example here. S3 must have a representation of degree 2, okay? So this degree, dimension of the underlying vector space, okay? So all representation of degree 1 are irreducible, but there are groups like S3 and representation of this group, like chi3 here, which have degree greater than 1. But my claim is that the reducible character of G are all of degree 1. There is S3 as a reducible representation of degree or character of degree 1. But abelian groups have all irreducible character of degree 1. Why is it so? Well, the reason is very simple. There are two proofs, proof 1 and proof 2 I have already given somewhere during the course, but I repeat it. And the proof 1 exploits the fact that the number of, if G is abelian, then the number of conjugacy classes of G is the same as the order of G. Because being abelian, okay, since G is abelian, conjugates are trivial. Okay, if you conjugate, I have to conjugate, right? I simply get the same element. So there are, okay, for all H, for all G and H in G, so there are order of G conjugacy classes. So there are order of G or conjugacy classes, but remember that the order of a group, okay, is the sum. Is the result we just used for S3 is the sum. Let's write it like this. So it's this fact that I've already quoted for S3. The order of a group is the sum of the squares of the dimensions of the vector space, of the irreducible CG modules, okay? But we saw that, let me show you again, that these dimensions, okay, are just the value of the characters in irreducible characters in one, okay? So by writing this, I'm writing the sum of the dimension of the irreducible squares, okay, of the irreducible representations. And okay, but remember that here G, in this particular case, the number of irreducible characters equals the number of conjugacy classes. So it's the order of G, okay? In this particular case, because this is abelian, so let's write it clearly, okay? It's not in general. In general, it equals, this does not hold in general. In general, the number of irreducible characters equals the number of conjugacy classes. Since this is abelian, the conjugacy classes, every element, every singleton is a conjugacy class. So this, the order of G equals of the order of G. So we have a sum, okay, of positive numbers, because these are dimensions, so these are positive numbers, which gives you the order of G, but the number of summands equals the order of G, okay? There is only one possibility for this to happen. So you have the sum of order of G positive numbers, whose sum is the order of G. The only possibility is that chi1 equal 1 for all chi in G. Okay, because as soon as one of these is larger than 1, you get a number that is larger than the order of G. Okay, so this is for abelian groups. All representations are linear, meaning of degree 1. Of characters are linear. Okay, representations are always linear by definition, by the use of words we have. But irreducible character is called linear when it's degree 1. Proof 2 we had already seen, but let's see it again. Proof 2 goes simply like that. If G is abelian of order n, of finite order n, then and rho is a representation, is an irreducible representation. Well, irreducible, but well, we'll do it in general, and then irreducible representation. Then, well, of course, rho G will be abelian, because it's the image of an abelian group. So if G has n elements, so let's say G1, Gn, okay, then rho G1, rho Gn is a finite set of commuting matrices. Okay, they pairwise commute because the element of G commute, so clearly under rho they still commute, and each of them can be diagonalized. Okay, is diagonalizable. You remember why? Because let's repeat it here. Because we know that in a finite group of order n, every element raised to the order of G is 1. So this implies that rho Gi G equals 1. That is, rho Gi is a root of the polynomial x to the order of G, which has n actually, okay, minus 1. This has distinct roots. And so this means that each of these is diagonalizable, okay? Because the minimal polynomial of rho of Gi has distinct roots, and this holds if and only if the rho Gi can be diagonalized, diagonalizable. I trust you are familiar with these things, but remember, if you want me to go through this argument anytime, just ask me. I will be happy to redo it. These are important facts of linear algebra that we are needing. Okay, so what we have? We have a set of diagonalizable matrices, finite set, and they commute. Then, an important result, the rho GI can be simultaneously diagonalized. There is a basis such that with respect to that basis, all rho GI are diagonal with respect to it. Each rho GI is of the form, well, I don't know, some lambda 1, lambda 2, lambda, just a second. Yes, K. Whatever. And then you see that this representation, this is an argument that is good for any representation of G, okay? But this representation, of course, is not irreducible. It's actually a direct sum of all the representations, this and this and this. This is just a special case of those blocks matrices we had. And so if rho is irreducible, okay, you see all the invariant subspaces. So the first basis element generates an invariant subspace, because if you apply any rho GI, you just multiply by an element here and so on. Okay, if this is irreducible, then this means rho GI equals something like this, a lambda depending on GI. I hope it's clear. I mean, if all the matrices are of this form with respect to the same basis, then this means that this representation is the direct sum of all these blocks, diagonal blocks, okay? There are plenty of invariant subspaces. This first subspace, the second subspace, the case subspace. And so if it's reducible, it has to be only one of these, say the first one, okay? So this is an alternative argument. It depends on linear algebra, purely linear algebra. Okay, so no matter what, whether the first or the second argument, there's even a third argument, but we have found that the reducible character of an abelian group are all linear of degree 1. And we are going to determine the representation, the reducible characters of a finite abelian group. First, note the fact that it's absolutely elementary. So let G be an abelian group of, let's repeat it, of finite order n. And let rho be an irreducible representation of G. So this means that rho goes from G to GLV. I could write C, but where the important thing is the dimension of V is 1, okay? So what's rho of an element G? It's a 1-by-1 matrix, okay? And what's the character associated to rho? Well, it's the trace of this matrix. But if you have a 1-by-1 matrix, its trace is just the element you find here, okay? Because the trace of rho G is just the element you find here, okay? And the chi, the associated character. So the difference between a representation of degree 1 and its character is just that the representation has bracket outs around the character, but they are really the same thing. In particular, it follows that the linear character so remember, linear character means linear character chi means chi of 1 is 1. Okay, I'll repeat this until you get familiar, meaning the dimension of the underlying vector space. Okay, the value of the character on 1 is the dimension of the right vector space, is a homomorphism, is a morphism from G chi to C star, okay? Because rho is a morphism from G to GLV. GLV is not exactly C star because it's given by non-zero. So what's GLV in this case? It's 1 by 1 matrices, since we determine a different from zero, means 1 by 1 matrices in which the element inside is a complex number different from zero, because of course the determinant of a 1 by 1 matrix is the number you find inside, okay? So if this is a morphism, this is also a morphism, okay? But these are called linear characters, morphisms from G to C stars. If you put bracket outside, you find a representation of degree 1. But important, a character of degree greater than 1 need not, it may be by accident, need not be a morphism. Okay, we can probably, if I remember, I'll have an example of this later. But so linear characters of degree 1, okay, remember this is called the degree, are morphisms because you just take the brackets from around the representation, the value of the representation, but characters degree greater than 1 need not be morphisms. We will probably see it when we get to S3, if I remember, or you remind me when I get there. Okay, good. So we are going to find these linear characters. Remember, degree 1 means irreducible. So what are the linear characters of an abelian group of finite order n? We'll begin with the easiest example. So to begin with, consider the case when, let me see whether I'm doing things right. Yes, the case when G is cyclic of order n. I'm not sure whether I'm using the order n, but good. So what are its characters? Well, remember, so let chi be an irreducible character, okay? So remember, this is a linear, so this is a homomorphism, just is what we saw on the previous board, okay? Then, so this is linear, chi1 is equals 1, just a second. And chi from G to C star is a morphism. Oh, well, a morphism of what? Of course, C star with respect to multiplication. Well, of course, C star is a group with respect to multiplication. There's no zero, so it cannot be with respect to addition. Okay, so of course, since this is cyclic of order n, we have that G to the n is 1, okay? So if I apply chi, which is a morphism. So remember, I could have applied the representation, but the difference between the representation is the character are just these brackets. So it's the same. I'm doing it without brackets, okay? So this is 1, okay? But this is chi of Gn. And since this is a morphism, okay? Let's underline this. It's a morphism. So this is chi to the Gn. There is chi G is an nth root of unity. Before I forget, this is one of the reasons why the theory of representations, group representations develop first on complex numbers. Then you have generalization coming in the ensuing decades. But in the complex numbers, we have all the roots of unity, okay, for any n. One good reason, well, to do this over C, which is algebraically closed and then has nth root of unity for all n. And actually, there are n distinct n roots of unity because it's important that it has characteristic 0, okay? Because as you remember from the algebra courses, in positive characteristic, for instance, in characteristic P, the only pth root of unity is 1, okay? The P, a prime number, is 1, so you have only one root. But here, given n, you have n distinct nth root of unity, okay? So Kg is an nth root of unity. Now there is an elementary fact that is proved in the group theory course that, okay, so you have a cyclic group of order n, okay? So let's do an aside, a discussion. So G cyclic of order n, okay? And H another group. For instance, in this case, I will use it with C star. How do I give a morphism? Well, F is probably a good enough name, from G to H. Well, the first observation is a general observation that if you have an element of order n, under a homomorphism, the image is order divided n. Okay, if F is given, so as usual, we are having a heuristic argument. We first assume that the morphism is given, and then we show how to construct them. If F is given, then as we saw here, it's the same argument, precisely the same argument. We see that Fg to the n has to be 1. I written in this order because this is how it comes out from this proof. It's the same proof I give here. Chi, after all, is just a morphism, okay? So remember, Fg to the n means that Fg is order divided n. So the image Fg of G is order dividing n, okay? So whenever you have a morphism, for the image of G, you need an element of order dividing n. I mean, dividing because, for instance, this could be the morphism that sends every element to 1. So, I mean, 1 to the n, of course, is n. It need not have order exactly n. Conversely, and this we are out of the heuristic argument, if H in H is order divided n, the map F from G to H given by G to the x equals hx is a morphism with Fg equal h. So let's see what I'm claiming here. I'm claiming that on the one hand, if I have a morphism from G to H, the image of an element of order n has to have order divided n. Conversely, if I take any element in H of order divided n, then this map is a morphism with Fg equals h. Well, of course, Fg is equal to h if you take x equal 1 here. Well, there is an important thing. The map is well defined, okay? It's well defined. And a morphism. Let's see this because it's elementary, but it's very important. So I'm claiming that F from G to H, where G is generated by G of order n, given by Fgx equal Hx is well defined. Why is it well defined? Because, I mean, you take the reason why it has to be to check whether it's well defined, because there is not a unique way of writing these elements. So suppose Gx equals Gy, okay? Then remember that two powers are the same if and only if x is congruent to y mod n, okay, of order n. Okay, so if this is equals to this, you have that this is congruent to x is congruent to y mod n. So what happens on the right? But then H, yeah, okay, fine. So remember, the assumption is that the order of H divides n. So if these two are congruent on n, okay, these are also congruent modulo the order of H, okay? Because the order of H divides n. So here I'm writing that the difference between x and y is a multiple of n. But if it's a multiple of n, it's a multiple also of the order of H, which is the divisor. And so this is equivalent. So this is just a left to right implication. Because I only have this divides this. No, let's write it well. I mean, that it is not get confused with an if and only if. Okay, now it's, okay. And so this means that hx equal hy. Okay, it's the same argument used here. These two powers are equal if and only if these are congruent modulo. The order of G, of the element G, which is of course the same as the order of the group G in this case. And so this implies this, and so these two are equal, okay? And then of course is a morphism, simply because, I mean, if you do f gx gy, the product, then you have x plus y, and then this f, this is h x plus y, and this is hx hy, where I'm using the power, the rules for computing with powers. No, okay. Okay, so it's a morphism. So this is an important, yet elementary yet important fact, that to give a morphism from a cyclic group over the n to another group, you just send G to any element of H you please, provided this element is order divided n. Okay, we have seen that this is a necessary condition, and it's also sufficient because of this argument. And remember the well definition, which is important. Good, but then the end result is quite easy, because you have an irreducible character, okay? An irreducible character means a morphism from G to C star, but actually the values it takes is in the set of the nth root of unity, which is actually a group, okay? So, no, well. So the irreducible characters of G, so cyclic of order n, are the morphisms chi from G to, it used to be C star, okay, I'll write C star on the right, but here we have seen that the values of the characters, well, on G, but then on its powers, is in the subgroup of the nth power, of the nth roots of unity. So this is omega, let's see whether I can use K, just a second. No, let's use I, okay, okay. So this is a subset, actually a subgroup of G. Let me give the definitions in a second, and I'll write something here, where omega is a primitive nth root of unity. So you may take, for instance, to be this, okay, the usual power, and I, well, I could let I run in Z, but I mean, if you want distinct elements, you just go from 0 to n minus 1. So this is the subgroup of nth roots of unity, which is a cyclic subgroup over the G generated by omega, okay? The subgroup generated by omega of nth roots of unity. Sorry, I wrote G, but since let me correct it visibly. This is really C star. Sorry for the misprint, but it's marked in red. So it's a subgroup of C star. Okay, the subgroup of nth roots of unity. And so, well, now it's very simple, because every element here in this group, we are called omega, okay, capital omega, okay, uppercase omega. Every element, now every element in omega as order divided n. Of course, the elements here need not have all order n. For instance, there's the identity 1 here, which has order 1. But for instance, let's say if n is 4, so a fourth root of unity, a primitive fourth root of unity is, for instance, I, the complex, the imaginary unit. It is squared is -1, which is order 2. So they need not have all order n, but they definitely have order divided n, okay? Because if you raise them to the n, you get 1. And so the point is, you can find, so the irreducible characters of G can be obtained simply by specifying. Remember, since G is a cyclic group of order n, to give a morphism from G to another group, you have just to assign the image of G to be an element of order divided n. Every element here is okay, because they have all order divided n, specifying K of G equal G to the, no, well, not G, come on, omega to the K, for some K. I wrote I here, but I could have written K, because I prefer to use this notation, okay? So this is, and then of course, once you have this, you have that omega G to the, chi G to the X is just omega chi X, okay? That's the value on all elements. So we found the irreducible characters. Let's take a couple of examples explicitly. Okay, the small example. This is just the case of the cyclic groups, mind you. Then we'll do the general groups. Okay, but this is already quite important because, I mean, you've probably studied Fourier analysis in some course in analysis. There is a discrete Fourier analysis which relies exactly on the character of cyclic or abelian groups. The Fourier analysis for finite groups, and these characters play an important role in that, because, I mean, similar to using the proper basis for the Fourier expansion. Is this one of the seminars? If not, I can add it for a seminar. So discrete Fourier analysis. I'll try and remember. Let me mark this down. It's a good argument because it comes straight, and it's very important in discrete mathematics these days. I mean, it's used. It has very important applications. So let's consider the simple cases. Well, okay, I have to do it. Let's start with a group of order 1, which is obviously cyclic. I'll write its character table. Ready? Well, okay. The character, actually, to be absolutely proper, I have to write 1 here. So what I mean here, so this is the one in G, okay? Number of conjugates. Sorry. Oh, let me. And there is only one character, and it has value 1, okay? Well, let's get this out of the way. Then suppose that G is cyclic of order 2. Okay, then the table becomes slightly more complicated because I'm not writing the number of conjugates, because since this is abelian, the number of conjugates is always 1. And the element of G are, of course, 1 and G, because then G squared is 1 again. So you have 2 characters. We know that they are linear. Okay, I write this because all characters are linear. Okay, so the first column is obvious. All characters are degree 1. And what can I do on G? Let's look back. G can be sent to any power of a primitive nth root of unity. In this case, omega is a primitive second root of unity, is -1, simply, okay? A primitive, because it's a square root of unity, which is not a first root of unity. And so I have to send, all my possibilities are to send G in one of the powers for k going from 0 to 1, because n is 2, okay? And so the possibilities are just this. This is a harmless looking table, but you see that it's quite important. By the way, you know that this matrix, if you look at inside this character table, is invertible. And then I'll give you an exercise to prove that this matrix is actually invertible. The character table, say, once you take off all this frame, is an invertible matrix. Okay, so this is a primitive second root of unity. Okay, let's make things a little more complicated. Cyclic of order 3. Okay, so this times we have 3 characters. Okay, remember, number of irreducible characters is equals the number of conjugate classes. This is abelian. So there are 3 conjugacy classes. Okay, so we have 3 characters. The elements of G, the distinct elements of G are 1G, G squared. Okay, so we have 3 characters. All linear. This is an abelian group, so irreducible characters are linear. And how do you define this? Well, you take omega. You know the form an irreducible, a primitive third root of unity. Which can be written explicitly because it's one of the roots of x squared plus x plus 1, of the polynomial x squared plus x plus 1. And so you have simply to choose on G, its value on G, okay? And remember, the rule is very simple. You can assign to G any power of k, of omega, from with a corresponding going from 0 to 3 excluded in 3. So 0, 1, and 2. Okay? And then what's on G squared? Well, chi, these chi are morphisms. Remember, because characters in general are not morphisms, but linear characters are, because they are just the representation with the braces removed, with the brackets removed. Okay, and so here we have 1 omega squared omega. And this should look familiar because this is a van der Monde matrix, okay? So you have 1 omega square, and this, here the squares, 1 square, omega square, square. Of course, this is omega. Okay, and let's finish with the groups of order 3. This will also be important. And of order 4. Well, we proceed slightly more speedily here because it should be quite obvious. The elements are 1G, G squared, G cubed, the distinct elements of G. All characters are linear, and you have to assign what's a primitive fourth root of unity. I, the complex unit, the imaginary unit, is a primitive fourth root of unity. I could have taken minus I, of course. And the idea is very simple. You simply write the powers of I. So 1I minus 1 minus I. This minus 1 will be important, as we'll see. And then you simply take the powers of this. So 1, 1. So I, this will be minus 1 minus I. This 1 minus 1. And this will be minus 1 and I. Okay, and this also, though written like this, is not immediately obvious, is a van der Monde matrix. It's because, I mean, after all, I'm taking these values, these are just the squares and the cubes, okay? So the square of I and the cube, the square of minus 1 is cube, the square of minus I and its cube. Again, a van der Monde matrix. Remember, there will be an exercise in which, if you take the character table of any group, this will be an invertible matrix. And you know that a van der Monde matrix with respect to distinct elements, and here you have 4 distinct elements, is invertible, okay? This is important, because the determinant is the product of all differences of the elements you have used to build the matrix. Good. So I think, so as you've seen, the theory of linear character, of irreducible characters of a cyclic group are relatively easy. you just pick an nth root of unity, and you draw the powers, and you get a van der Monde matrix. So you find again a familiar friend, this van der Monde matrix. And now the problem is, what do you do with a general finite abelian group? And we will discover that we have already done most of the work. It's just technicalities from, it's downhill from here. It's just technicalities. But first, we have to make a remark. The remark is the following. Let G be, for the moment, any finite group. Okay? Let chi1, chi2 be two, say, two characters of G. Okay? Consider their product. What's this? This is a function chi1, chi2, which on G is just the product of the two functions. Pointwise product. Okay? So chi1, chi2 is a function from G to C. And note, since chi1 and chi2 are class functions, they are invariant. They are constant on conjugate classes. Also, the product is a class function, okay? Because clearly, if you replace G with a conjugate, then the values of this are the same, so the value is the same. So, and chi1, chi2, sorry, the product, chi1, chi2 will be another class function from G to C. So I write it from G, but it's really from the set of conjugacy classes, if you wish. And say, no, okay, so it's a function on G which is constant on each conjugacy class. We will see, this goes with through tensor products, but I don't want to do this now. We will see that chi1, chi2 is actually another character of G. So characters of G are closed under product, and also under sum, because this is the direct the sum. But this is obvious. This requires going through tensor products. We'll do it in time. Mind you, the product of two irreducible characters need not be an irreducible character, okay? So it will be a sum of irreducible characters. Perhaps just as a brief aside, we've seen that there is some sort of duality between irreducible characters and conjugacy classes. I mean, to begin with, there are as many conjugacy classes as irreducible characters. Now we see that the product of two characters, well, I just mentioned it. We will see that the product of two characters is another character. And it's easy to see that if you have two conjugacy classes of a group G, you can take their product, meaning the set of the products, one element in the first one, and one element in the second, and this will be a union of conjugacy classes. So something similar to this. And some mathematicians, friends of mine, developed over some decades a theory called table algebras, which tries to find the exact parallels between what's going on in characters with products and what's going on in conjugacy classes, because there's some sort of duality. I mean, you can do things on one side and on the other side. So there have been developments in that direction. I mean, relatively recent research. Okay, so we will see that this is another character, but for the moment we are content with considering a special case. Okay, and so what we do, so let let me use, let chi be a character of the group G, which is arbitrary at the moment, not necessarily abelian. And lambda be a linear character of the same group G. So a character of degree 1, which is then irreducible. Then I'll prove that lambda chi, with this definition, then is in another character of G. Moreover, if, okay, let's call it a proposition, okay? The product, the proposition starts here. Sorry, I tend to state everything as facts, but of course it's important now and then to state clearly, to make clear statements to be reused later. Just a second. Okay, fine. If chi is reducible character, then so is lambda chi. Okay, good. Let's prove this, and the reason it's quite simple, because so I have taken a character. So chi of G is the trace of well, sometimes I write. Let's try. I'll try to write trace in full. Rho G for some representation. With, remember, is a morphism, okay? And then lambda is a linear character, so lambda is also a morphism. And lambda from G to C star, a morphism. Okay? And then you consider a representation, say theta, from G to GLV, no, it's from capital G. What's this? So theta of G is simply given by lambda of G, rho of G. This makes perfect sense because this is a complex number and this is a matrix, okay? And so you are multiplying, okay, let's say the dimension of V is, let me use D, okay? A D by D matrix. And I'm multiplying it by a scalar. So this is again an element of GLV, okay? Because you're multiplying, well, actually, this is different from 0, no? Right? So this is still an element of GLV because the determinant will be this number, which is non-zero, times this number, the determinant of this, which is non-zero, okay? So, okay. And then this is a morphism, still a morphism. Why? Because you take theta of GH, so by definition this lambda GH, rho GH. And both rho and lambda are morphisms. And this is important, these are scalars, okay? And remember that whenever a product of matrices and you have a scalar, the scalar is represented through a scalar matrix, okay? So multiplying a matrix by a value, say lambda, is like multiplying it by the scalar matrix, which is a lambda, lambda, lambda on the diagonal. So this you can think of this as scalar matrix. Remember, this is in the center of GLV, okay? They commute with homoscedes. I mean, they commute with everything. So you can exchange this. Okay, and this is just theta of G times theta of H. So it's still a morphism, okay? And yes, just a second. And it's, well, okay. I also claimed that one is irreducible if one is irreducible, then so is the other. Okay, sorry, no. First, let's finish this. So this is still a morpheme. So theta is still a representation. And its character is, what is its character? Is the trace of theta of G, okay? So it's a trace of lambda G rho G, but this is a scalar, okay? And the scalar can be pulled out of the trace. The reason being, let me write it on the next page, okay? Because if you have a matrix, okay, with certain elements on the diagonal, and you multiply it by a scalar, it's not important. Since we want to take traces, it's not important what we have around here. You end up multiplying each element by lambda, okay? And so if you consider the trace of this is just trace is lambda A11 plus lambda ADD, and so it's just lambda. I mean, you know that the trace is a linear function, okay? And this is the trace of this matrix here. So you just multiply it by lambda. Okay, it's obvious, you know it from linear algebra, but so the trace of this will be lambda of G, trace of rho G. And remember that the trace of rho G is just chi. Okay, so we found that this is also a character. So I proved a very special case of this more general fact, that if you take a character, any, and the linear character, 1 of degree 1, then their product is another character, okay? In general, as I said, the product of two characters won't be, of two irreducible characters won't be irreducible, but here if chi is reducible, then so is lambda chi, and we'll see it in two different ways. Remember, lambda is linear, so it's reducible. If chi is reducible, let's see that lambda chi is irreducible, okay? If chi is irreducible, then so is lambda chi. Two proofs. The first proof is just a standard linear algebra proof, and then we'll have a magic proof via characters, okay? So the reason is very simple, because to say chi is irreducible, so remember that this is an important fact. I mean, we have two weeks to review what we've done so far, but you can read the irreducibility for a representation from the character. And so you can say that chi is irreducible if and only if rho is irreducible. Okay? But this means that there is no subspace. Well, I'll have to continue here. U comprised between 0 and V, which is rho G invariant. Okay? But you see, every subspace is invariant under multiplication by a scalar matrix. Because by definition, because a subspace is something that such that if you take an element in it, then the multiplication by a scalar is still in the subspace. It's the definition of a subspace. So if there are no subspaces invariant under rho G, okay, there is under all rho G for G in G, then this is equivalent to say that there is no subspace U like this, okay, invariant under lambda G, rho G for all G. Because if it's invariant under rho G, then of course it's invariant under multiplication by a scalar, okay? Because it's a subspace, okay? And so you see that this means exactly lambda chi is irreducible. Okay, because multiplication by a scalar leaves every subspace invariant. I mean, by definition of subspace, linear subspace. So if this is invariant around the rho g, so invariant under lambda g rho g, and conversely, because I mean you go from here to here, multiplying by the inverse of lambda g. So this is the proof one, linear algebra. But people working with characters tend to do everything with characters, and so let's use character part two. So we want to prove chi is irreducible, guacamole, if and only if lambda chi is irreducible. I'll just do one implication, because I mean, you go from here to here multiplying by lambda, you go from here to here by multiplying by lambda inverse. But so chi is perhaps, well, okay, reducible means, well, there is an inner product that chi is 1, okay? What's this? This is the sum, this is the average over G, summing over G, of chi conjugate of G, chi G, okay? Good. So chi reducible means that this inner product is 1. Let's consider this inner product. Okay, so this is 1 over G, sum, G in G. You have lambda G, because remember that lambda chi, the value of the product is just the product of the values, by definition. So you have lambda G, chi of G, conjugate, lambda G, chi of G, okay? But let's rearrange things. These are just numbers. This is sum in the complex number. Okay, and but remember, this is the value of the character over an element, okay, of a linear character. And we have just seen in the representation theory of abelian groups that the value of lambda on G, so if G has order n, lambda G equals, let's call it omega, okay, where omega is a, not a primitive, but an nth root of unity. Okay? So lambda G conjugate will be omega conjugate. But we know that for roots of unity, okay, well, of course, roots of unity have modulus 1. So what's the conjugate of a root of unity is just the inverse, okay? It's a familiar fact because you are in the complex plane. You have an element here on the circles of radius 1, and the conjugate is this, but this is also the inverse, okay? If you look at how you conjugate, since a root of unity has modulus 1, okay, the product is just done by summing the angles. And so if this is omega conjugate, which is on the other side, and the angles cancel out. So the product is exactly 1. This is the inverse, okay? And so what we get here, that this product is 1, okay? So let's write it here in red because it's a bit on the corner. So lambda G, lambda G conjugate, lambda G is nothing else but omega conjugate omega, omega minus 1, omega is 1, okay? So each of these factors cancels out. We see, we have seen, well, okay, because these are nth root of unity. And so what we get here, these factors have cancelled out. The sum is not important. The sum, each single factor here cancels out. And we've seen exactly the same values here, okay? Well, let's not write this equality here, but this is 1 because it's chi-chi, okay? So you see the linear characters part has disappeared because of this property of roots of unity. So we've seen a particular case of a more general fact that we will see later, and namely that if you have any character and a linear character, the product is another character and it's irreducible. And if one is irreducible, then so is the other. Okay. Good. Just a second. Okay, so my goal. Well, okay, let's finish with this, and then we'll resume on the 12th. Now, if G is a finite abelian group, then we've seen here G is made of linear characters, okay? And the result we've just seen tells you that if you multiply a character by a linear character, you get another character. If you multiply two of this linear character, you get another character, which is a linear character. So it's closed under the product. Okay, because it's enough that one of them is linear for the product to be a character, and of course, if lambda 1 and lambda 2 are linear, then so is lambda 1, lambda 2 the product, because when you compute this on 1, by definition, this is lambda 1 of 1, lambda 2 of 1, okay, and this is 1 times 1. 1. Okay. If you have two linear characters, meaning calculating on 1 you get 1, then also the product is a character. So here G is closed under a product, but actually here G is a group under this product, the product of characters. This is called the dual group. And we will see in 2 weeks' time that this group is isomorphic to G, although not in a natural way, somewhat as in for the case of the dual vector space. Let's just see why this is a group. The unity is the trivial character. I've already called it the trivial character. No, sorry, not the trivial product, the trivial character. What's this? It is the character that has value 1 for all G in G. It's clear that this is the identity because sorry, let's change notation. Let's call this to be trivial. Let's call it tau, okay? Because if you do tau chi, well, chi is any character of G, then you have tau of G, chi of G, and since this is 1, you get chi of G. Okay, so it's visibly a unity. And what about inverses? Well, if chi is in here G, remember this is abelian. Let me check whether I wrote abelian. Yes, abelian. Yes, in here G. So chi from G to C star is the morphism. Okay, then chi inverse is still in here G, where chi inverse of G is just chi G inverse. Why is it so? Well, it's quite simple, because so an irreducible character is just a morphism from G to C star, okay? So if you compute chi inverse of GH, you'll get what? You'll get, by definition, chi of GH inverse. Chi is a morphism. You have an inverse here. Normally in algebra, you have to be careful because when you take the inverse of a product, it will be the product of the inverses in the reverse order. But C star, of course, is an abelian group. So we just have this, which is exactly chi inverse computed on G and chi inverse computed in H. And of course, you'll see immediately that chi times chi inverse is the trivial character, tau, the trivial character. So what we have found, we have just, I'll be back on this page. We have found that the reducible character of finite abelian group are a group under this product, okay? And it's called the dual group. And we will see that this group is isomorphic to G. And we'll describe the group and we'll see that it's not terribly difficult, but we'll do it in 2 weeks' time.